My name's Luke.
Hey, and I'm Ben.
And today we're going to be talking about passive filters with a low and a high pass.
Yep, we're going to do a diagram on paper, and then we show you that schematic. We're going to go on to LabVIEW and then show you an actual circuit.
All right, let's dive right into it.
There we go.
Alright, so here's a brief pen and paper example of our passive filters that we're going to be using today. Now the difference between an active and a passive filter compared to last week is this circuit does not have an op amp in it. Our V out is between our resistor and our capacitor, and our V in is obviously going to be this wire right here coming right from our power supply. To calculate our V out, we actually found that it's a voltage divider. If omega is approaching 0, we find that H is going to be equal to 1 over 1, so that gives us a magnitude of 1 and a phase of 0. If omega is approaching omega naught, then we find that H is going to be 1 over 1 plus J, which gives us 1/2 minus 1/2 J. So we get a magnitude of 1 over the square root of 2 and a phase of negative 45. If we find that omega is approaching infinity, we find that H is equal to 1 over infinity multiplied by J, which gives us a negative 0J. We actually find that our magnitude is 0 and our phase is going to be negative 90 degrees. Alright, so here we have our high pass filter, and it's set up relatively the same. The difference is our capacitor is before our 1 kilo ohm resistor. If omega is approaching 0, we calculate out that H is going to be equal to 0J. So again, our magnitude is going to be 0, but our phase is actually going to be a positive 90 degrees. Omega is approaching omega naught, we find that H is going to be equal to 1/2 plus 1/2 J. Our magnitude is actually going to be 1 over the square root of 2, so we get a phase of positive 45, approaching infinity, so we get a magnitude of 1, and a phase of 0 degrees. One thing that we wanted to calculate out was what would our magnitude be at omega naught. After we calculate that out, we get 159 hertz for our frequency at that point, which Ben will explain real quick in an LT Spice simulation.
Here's our LT Spice simulation for our low and high pass passive filters. On the left here is our low pass filter. Right now we have the cursor set up to read the value at 707 millivolts. At that point you can see that our frequency is 158 hertz and our phase is about negative 45 degrees. And the reason why the frequency is a little bit off is because it's off by a factor of 2 pi. If you multiply this by 2 pi, you're going to get almost exactly 1,000 hertz, which is what we calculated mu naught to be. Again, as you can see, our value for our output voltage, which is in blue, goes from 1 volt to 0 volts, goes from a phase of being in phase to being behind by 90 degrees. On the high pass filter, the phase of the voltage starts leading by 90 degrees and goes to in phase, whereas the voltage goes from 0 up to 1 volt. Match our VN, omega naught has not changed and the frequency is still the same. Phase for the high pass filter is 45 degrees because the out will actually lead VN.
Here we have our circuit, and how we have this set up is our DAC is actually controlling our function generator through the exterior input. We then get an output from our function generator that runs to our breadboard through a positive and our ground right here, and then our power is going from there into a 1 kilo ohm resistor, which then goes to a 1 microfarad capacitor and then back to ground. What's very important is what's in between those two components. And what we're measuring with our orange wire right here, which again is hooked up respectively through our DAC, is this is our V in, and then between the resistor and the capacitor through the purple wire, which is also hooked up to our DAC, is measuring our V out. So here's the ports on our DAC. Here's how we're powering our function generator through ports 15 and 16, which for our V in, we're going to be using the orange wire, which is going to be port number 4. For our V out, we have it set up to port number 1, and then again, grounded out respectively. This is our function generator after we ran the VI, but when we start the VI, we actually see that the frequency will rise, which is being controlled by the computer. Here we have our VI, our DAC assistant that is reading in the data. This is our DAC assistant that is outputting a signal to power our function generator. After it goes through the entire course of the VI, it will show up on a Nyquist plot and see the frequency increasing. Once this is all said and done, we see the graph right here shows us that the magnitude goes from 1 to 0, and the phase goes from 0 degrees to negative 90 degrees in a clockwise direction. So now that we have this set up for our high pass circuit, we can go ahead and run it They're starting 90 degrees out of phase, and by the time this finishes up, they should be completely in phase. You can see the waves slowly falling into phase. And you can also see the magnitude getting higher and higher as time progresses throughout the VI. So now that we're all said and done, we can see our plot on the Nyquist plot. What is actually happening is our phase is starting at 90 degrees, leading V in, which is full imaginary, and it's going to end up all the way real over at 0 over here. We can also see that our magnitude is going from 0 to 1 as the VI progresses and the frequency increases. So basically what will happen is it'll be an entire circle depending on if it's high pass or low pass. So that's a little bit about low and high pass passive filters, and we hope you learned a little bit about how we calculated the magnitude and the phase. And as always, we really appreciate your time, and we'll see you next week.